Okay, so I'd like to thank the organizers for inviting me to give this talk. So this is work done entirely in ISC. There are 4 experimentalists involved and 2 theorists. So Abhishek Banerjee actually did a lot of the experimental work, and Oindrila Deb did a lot of the theoretical work. There's also Kunjalata Maji, so they're all in the audience, and Ganeshan and P.S. Anil Kumar. So the outline of the talk is as follows. So first I'm going to present the experimental observations and analysis. So these involve thin films of bismuth selenide nanocrystals. So you'll see exactly what I mean by this. Then I'll present the magnetoconductance data, the surface penetration depth, and spin orbit coupling and Berry phase. So this is all experimental stuff. And then at the end, I'll present a very simple model which qualitatively explains all of these observations. Not really quantitatively, but at least qualitatively, it really explains all of them. And this system, we have called this a granular topological insulator for reasons that will become clear. Okay, so the system is sort of like this. So you have to imagine that there are sort of a thin film. So the thin film can have a width ranging from 30 nanometers to 150 nanometers, something like that. And this film consists of lots of grains. Okay, so these grains are stacked as a 3-dimensional array. Okay. So this is first of all a picture showing the surface topography. So each of these is a separate grain, and so you can see that it looks fairly randomly distributed. However, it's not really that random because there is this X-ray diffraction scan, and along these directions, 003, you can see that there are these peaks, which basically tell you that there is actually a preferential orientation along the C-axis. The C-axis being the axis along which the bismuth selenide molecules are lined up. There's also this scan of the 105 planes of bismuth selenide, and that shows there is a 6-fold symmetry. So it means that the grains are actually, the alignment in the C-axis is fairly regular. There is also this reciprocal space map in terms of QZ and QX. And this scatter shows that this system actually has a large degree of granularity. So these nanocrystals typically have a thickness in the C-axis about 2 to 3 nanometers. And in the XY direction, in plane size, it's about 10 nanometers. So that's dimensions of each of these nanocrystals. And then you have to imagine that all these nanocrystals, they form an array in the XY plane. And then there's another array on top of that and another one on top of that. And then the entire film has a thickness of 30 to 150 nanometers, the different samples, which means that the entire film will have something like 10 to 50 layers of these bismuth selenide arrays. Now, so the main observations are about the magnetoconductance of this system. So to appreciate that, particularly for the students, let me just say a few words about weak antilocalization. So it's known that for electrons which are governed by the standard Schrodinger equation, non-relativistic, they show positive magnetoconductance. So that's weak localization. But for electrons which are governed by the massless Dirac equation, which happens to be the case at surfaces of topological insulators, magnetoconductance is negative for small magnetic fields. So why does this happen? So at zero field, if you look at the possible paths that an electron can take, starting from some point, going somewhere and coming back. So think of a path like this, it starts here, goes around and comes back. Now, for every such path, there is a time reverse path which goes in the opposite direction. And when electrons obey the Dirac equation, it turns out that the relative signs of these two paths is exactly -1 if there's no magnetic field present. Okay? So this is the alternative way of stating this is that you can calculate a Berry phase, which is the phase picked up by the wave function of the electron when it goes completely around, and that's equal to pi. And so these two paths exactly cancel. So because these pairs of paths, which are time reverse versions of each other, cancel, the probability of returning to the same point, which is the sum of the two paths modular squared, is reduced compared to what it would have been if there was no such cancellation. So if the probability of coming back to the same point is reduced, then that means there's less resistance and higher conductance. Now when you apply a small magnetic field, so let's say, think of this perpendicular magnetic field. So then these two paths, they enclose some flux, but they enclose the flux in with two different signs, because these paths are, one is clockwise and one is anti-clockwise. And so the Arnold-Bohm phases of the two paths are opposite in sign, which means that the relative phase between the two paths is not pi anymore. So now these two paths don't exactly cancel each other, which means the probability of coming back to the same point increases a bit and the conductance decreases. Now this is, you'd expect this to be most prominent for paths on the top surface in the presence of a magnetic field, but it happens even for the case of the magnetic field being parallel to the surface, because there are paths which go into the bulk of the system and then comes back to the top. So you'd expect sort of this negative magnetoconductance or weak antilocalization even for both perpendicular. Oh yeah, did I say that wrong? Yeah. So in the presence of a magnetic field, the conductance is reduced, it is more localized. So at zero field, it's anti-localized. Yeah, yeah. So this word anti-localization covers zero field, yeah. Okay, so now let me show you the data. So this is for a variety of thicknesses. Okay, so it's actually 8 nanometers to 150 nanometers. And this is a change of the conductance from the zero field value. So you can see in every case, as you increase the field, whether it's positive or negative, the conductance decreases. So that's negative magnetoconductance. Now given this data, there are two quantities that you can calculate by fitting the magnetoconductance to this famous formula by 3 people, Ikami, Larkin, Nagaoka. So it's a complicated formula. This is the digamma function. And so there are 2 parameters which appear here. One is the phase coherence length, which is L phi. And then there's this parameter which I'll call alpha perpendicular, because this is for the case of the perpendicular field. So by fitting this, you get this alpha perpendicular to be of this form as a function of the thickness. So you can see that for small, very thin films, it's about 0.5. For very thick films, it's around 1. And the dependence on the temperature is not very large, but there's a strong dependence with the film thickness. So just to show you what this phase coherence length looks like. So here's a picture of the phase coherence length, and it's actually quite large compared to the film thickness. There seems to be some scaling law with the temperature. So at low temperatures, it's as large as 75 nanometers. Okay, then you look at the magnetoconductance data for parallel field configuration, and this time you fit this to a different variant of the HLN formula, which is of this form. So here, the 2 things which appear are, as a function of temperature. So it decreases with the temperature as you, increasing temperature as you expect. So here the fitting gives you this another parameter, which is alpha parallel, which again goes from 0.5 at low thicknesses to 1 at high thicknesses. Another parameter which appears here is B phi. So this is a combination of the L phi, the phase coherence length, which we use the same value that we got from the perpendicular field magnetoconductance data, and then something else, lambda, which we can interpret as the penetration depth of the states into the bulk. Okay? So because this magnetoconductance for parallel fields basically comes from for paths which go into the bulk a certain distance lambda and then come back. Okay? So you'd expect that to depend on the surface, the penetration depth into the bulk of these states of the system. So an interesting thing that appears at this point is that if you compare these two alpha parameters, the alpha perpendicular and the parallel, they look very similar. I mean, they both start around 0.5 at small thicknesses and go up to 1. So So the interpretation of this change from 0.5 to 1 is as follows. For thick films, they have this value of 1, which implies the presence of 2 decoupled surface states. So now these are surface states of the entire system. So the system has lots of grains, but here we are talking about the absolute top surface of the system and the bottom surface of the system. Okay. So, so at large thicknesses, it looks like there are 2 decoupled surface states. Whereas for thin films, the value of 0.5 suggests that these surface states have hybridized. So this is actually a complicated story of going from 0.5 to 1. So there is this very detailed article by Garate and Glassman which actually derives the expressions for alpha for various regimes of film thickness, phase coherence, length, and so on. But that's the interpretation of these values 0.5 and 1. So basically it means that for thick films we have 2 decoupled surface states, top and bottom surfaces. For thin films, these 2 are coupled to each other. Yes, I don't know. So Abhishek, do you have? The other important parameter which appears here is this lambda, which I said can be interpreted as the surface penetration depth. And so this looks like this. So you can see that it actually decreases when you increase the temperature. For every film thickness, except for these thinnest films, it decreases substantially as you increase the temperature. For very thin films, 8 nanometers, lambda itself is of the order of 18 nanometers. So then there's not much scope of this penetration depth changing with temperature because it's already of the size of the thickness of the film. But if you increase the film thickness, then this lambda increases but eventually saturates at around 35 nanometers, which is much less than the thickness at that point. And then it decreases with temperature. Now, striking thing to observe here is that these lambdas that you observe in this system are much larger than in a single crystal of bismuth selenide, where lambda is typically 0.8 nanometers. So that's one of the puzzles. Where do these very large surface penetration depths come from? So what this means is that the surface states from the top and bottom, they actually penetrate into the system through a distance which is actually several grain sizes. Okay, so they're not cut off by a single grain size. They actually penetrate something like 40 grains into the system. So that's one thing that we have to understand. Another thing you can look at is the effect of the Zeeman field. Okay? So this magnetic field, so the magnetic field actually has 2 effects. One is that it affects the orbital motion, okay? And that's where you get this weak antilocalization, the effect on the Berry phase and so on. But they also couple to the spin of the electron, and so that's the Zeeman coupling of the magnetic field to the electron. And that also affects the magnetoconductance. So as I said, the electrons on the surfaces of a topological insulator are described by the Dirac equation. So we'll see this in a little more detail in a while. And so the dispersion is like this. So it's like, is the dispersion of a massless Dirac equation. E is some Fermi velocity times the magnitude of K. And for that, as I said, the Berry phase picked up on going around equal energy contours. So at a fixed energy, if you go around the momentum along a closed curve, the phase picked up is pi, provided that there is no magnetic field present. Now, if there is a magnetic field present with a Zeeman coupling, then the Berry phase changes from pi. And phenomenologically, this has been, I think, done by other people, but this was used here also. This modifies the HLN formula in this way. So there is this, effectively there is a correction to this coefficient alpha, which is of this form. It's quadratic and be perpendicular. It has to be because, it should have the same value for positive and negative values of perpendicular. So it can't be linear. Okay, so there are 2 things here. So there is this correction, and then from this correction, you can, what appears is some ratio of the applied magnetic field to some other effective field. This effective field is what we call the effective spin orbit coupling. So this is basically just the value of the energy of the electrons, the distance of the electron energy from the Fermi point, or from the Dirac point, sorry. So Vf times Kf. Okay, so by fitting this to the Zeeman field, you can actually pull out this quantity, the effective spin orbit coupling, BSOC. So here's a plot of that. So you can see that the effective spin orbit coupling, this increases with increasing temperature for every film thickness. It also increases with film thickness a little bit at low temperatures, but quite a bit at high temperatures. You can also figure out how the Berry phase changes. So you can see that it changes away from pi as you increase the magnetic field. Okay, so that's sort of the experimental data that I wanted to present. Any questions should be directed to Abhishek. Yeah. Distance between two oh, the single crystal, by that I meant a really big crystal. So very, very thick crystal. Yeah. So if you take a very thick single crystal of bismuth selenide, then the surface state penetration depth is 0.8 nanometer. Now in this system, the grain size is typically the thickness. Yeah, so here the thickness is about 2 to 3 nanometers per grain. And then we are assuming that the grains, the two separate grains almost touch each other. So there is not much distance between two grains. Okay, so now I'll tell you a little bit about the theory. So let me start from really the macroscopics here. So bismuth selenide, a single crystal of that, it has a Hamiltonian near the gamma point, the origin 0, 0, 0 of the three-dimensional Brillouin zone. It has a structure like this. Okay, so there are the spin Pauli matrices sigma x, sigma y. I think I may have missed a sigma z over there. So you have the Pauli matrices appearing. Then you also have the tau matrices. So these tau matrices are pseudo spin matrices. So they're 2 by 2, and tau z plus or minus 1 denote electrons on bismuth and selenide. Okay. So here the electrons basically have 4 components: bismuth, selenide, spin up, spin down. And there are 2 velocities which show up. So V parallel is the velocity in the xy direction, and Vz is the velocity in the z direction. And then there is this parameter m. So these are the values of the parameters, all written in units of eV and nanometers. So if you look at the bulk, you'll find that in the bulk, the spectrum is really gapped. And the gap is 0.28, this m, 0.28 eV. Then if you look at the surfaces, so now imagine that this crystal actually is not infinite in size, but it has surfaces. You find that on the surfaces you have states which are separated from the bulk states by a gap, which is this m. And these surface states actually appear on all surfaces, top, bottom, side, all possible free surfaces there. These surface states decay exponentially as we go into the bulk. And the decay length, so for example, if you're looking at the top and bottom surfaces, which are the xy planes, on those surfaces, the decay length is, you can actually solve for the surface states from this Hamiltonian. You find that the surface state decay length is given by this h cross Vz by m, so this is 0.81 nanometers. So this is the figure I quoted earlier. Then the surface states are described by massless Dirac equations. So they're most simple on the top and bottom surfaces, xy planes. You also get Dirac equations on the side surfaces, but they're more complicated. So at the top surface, this has this form h cross Vf, sigma x ky minus sigma y kx. Bottom surface is the same with the minus sign. And this Vf here is actually the V parallel, so it's 0.333 eV nanometers. So an interesting thing about this particular Hamiltonian is that if you find the eigenstates and eigenvalues of this, you can see that the direction of the spin and the direction of the momenta are related to each other. So they show what is called spin momentum locking. So the spin and momentum are mutually perpendicular. So for example, if you are at a positive energy, so this is a plot, this is kx, ky, and the red arrows show the direction of the spin. So if you are at positive energy and let's say kx is positive, so you are here, then sigma y has to be negative so that this whole thing is positive. So if kx is positive, sigma y is negative. Then if you go here, kx is 0, but ky is negative, and then sigma x is negative. Okay. So basically this tells you that the spin is always perpendicular to the direction of the momentum, and it's perpendicular with a certain handedness, okay, which is opposite on the top and bottom surfaces. Okay, so by the way, there are two nice review articles about topological insulators in general, and a lot of these parameter values can be found in this first review article. Okay, so now I come to our model of a granular topological insulator. So the first thing we do is that for the individual nanocrystals, the bulk states are separated from the gap by this, separated from the surface states by this gap. So first thing we do is we ignore the bulk states of each nanocrystal. So we just keep the surface states of the nanocrystals. Okay, so now this is like a schematic picture of the system. So you have all these grains, they're in a regular array. The real system is not that regular, somewhat regular in this C axis, but not so regular in the XY axis. But this is our idealized model. So we just take a regular array of individual grains. So you can see that you have a single grain, and so which has all these surfaces. So we introduce a coupling between the opposite surfaces of the same grain. Okay? So that's the intra-grain coupling that we call that T1. So that's between the two surfaces of the same grain. Then we also have a coupling between the neighboring surfaces of two neighboring grains. So if I just blow up this, so this is in the vertical direction, but I'm just showing that horizontally now. So within the opposite surface of the same grain, we have a T1, and the neighboring surfaces of two grains, we have T2. The intergrain coupling. And then if we think of this as a regular array, so with a unit cell size of, let's say, L, so which is 2 to 3 nanometers. Okay, so that's our model. It just consists of surface states of the different grains coupled by T1 and T2. Okay, so now let me just label these surfaces. So let's say this is the top surface of the entire system, this is the bottom surface, and there are all these grains. Let's call these top surfaces of each grain as 1 and the bottom surface as 3. Now this T2 is a coupling between two different grains. So this involves changing the number of electrons in the two grains. So you'd expect that this would have a barrier given by the charging energies, because this is changing the number of electrons in the two grains, so there's a charging energy of the grains associated with this. And so this tunneling of an electron from this surface to that surface has a barrier, and you would expect that to have an activated form with respect to the temperature. On the other hand, so you expect T2 to increase with increasing temperature. E to the power minus some delta by kV. On the other hand, T1 is the coupling between the two surfaces of the same grain, so that doesn't change the number of electrons within that grain. So that should not have a really significant temperature dependence. Okay. So now the Hamiltonian governing all the surface states is given by this, of this form. So these are the surface state Hamiltonians that I wrote down earlier. Then there's a coupling T1 between the two surfaces of the same grain N, and T2 coupling between surfaces of N and N plus 1. If there's a Zeeman field, then you have to add a term like this to the Hamiltonian. Okay. So first of all, let's look at this one without the Zeeman field and look at what the energy spectrum is for that part of the Hamiltonian. So now you discover that the system as a whole has bulk states. So these are not the bulk states of the individual nanocrystals which we have thrown out before. These are bulk states of the entire system. So they go across all the grains. And that has this form. And so you can see that the minimum possible value of this is you put kx, ky is 0, and you look at this expression, you find that it has a gap which is T1 minus T2. Okay. So the system as a whole has a bulk gap. In addition, you find that there are states at top and bottom surfaces if T1 is less than T2. So I'll call that the topological phase. And there are no surface states if T1 is bigger than T2. So that's the non-topological phase. You can also work out what the surface state penetration depth lambda is, and it's given by this. So e to the power minus L by lambda. So L is the unit cell size. So you have to have that length scale showing up here. So e to the minus L by lambda is T1 by T2. So what you observe from here is that as the temperature increases, T2 also increases. So this thing decreases, which means lambda decreases. So that means that as you increase the temperature, the surface states become better and better defined because they have a shorter penetration depth. So the surface states at the top and bottom get more decoupled from each other. So you have this peculiar result that as you increase the temperature, the system goes deeper into the topological phase. Now, of course, this has to break down as you increase the temperature too much, but at least in the range of temperatures that where the experiments were done, as I showed you, this gives you this funny result that the increasing temperature makes it more topological. Yeah. Okay. So here's just some pictures of the surface states for T1 fixed at 0.2 eV and two values of T2. So you can see the larger value of T2 has shorter decay lengths. Okay, now if the two surfaces are well separated, then the surface states have this dispersion. This has a degeneracy of 2 because of the two surfaces, top and bottom. But now if you have a finite separation between the surfaces, that means finite thickness of the film, the states will hybridize and will get this. Okay? So there's a gap now, and this gap is related to T1 and T2 in this form. So the point to note here is that apart from some factors in front, it's T1 by T2 to the power n. So this decreases exponentially with the film thickness as you expect. Right? The film thickness is n times L. So the thicker the film, the smaller is the gap. As the smaller is the hybridization between top and bottom, so the smaller is the gap. So this is a picture. So these blue lines are the bulk states of this entire system as a function of the magnitude of K, Kx or Ky or square root of it. And these red ones are the surface states for this set of values, T1.2 and T2.25. So now if you increase the film thickness or the temperature, the surface gap decreases because the T2 increases. So since the Fermi energy is fixed by the conduction band bottom, so the EF is fixed. So if you decrease gamma, then this part has to increase. So this explains why the spin orbit coupling will increase with the film thickness or the temperature, which is what you observe experimentally. Then you can look at the Berry phase. So you can do this calculation of the Berry phase. So when you turn on the Zeeman field, you find that the surface state dispersion has this form. So this is a familiar form that we saw before. The extra term is Bz plus minus gamma squared. So Bz is some dimensionless quantity built out of the Zeeman field and the gyromagnetic ratio and Bohr magnetron. Now there are actually 4 states here because you can have plus minus and plus minus. So you can calculate the Berry phase for any one of these 4 sets of states. So as I said, it's given by an integral around a contour of constant energy. So if you parameterize Kx and Ky like this, the Berry phase is this integral of this angle theta 0 to 2 pi, psi dagger del psi by del theta. So there is a standard formula for calculating the Berry phase. So for these 4 sets of states, you find that it's given by this. So when the Zeeman field and the hybridization is absent, then this is pi as we expect. But as you turn on the Zeeman field or make the film thinner so that gamma increases, you shift the Berry phase from pi. So the effect of Zeeman coupling is like this. So assuming that the surface hybridization is small compared to the Zeeman field, you find that the deviation of phi from pi is proportional to Bz, and therefore you get this modified HLN formula. This B perpendicular divided by B SOC is essentially Bz in some dimensionless times some dimensionless numbers. Okay, so this sort of qualitatively explains where this formula comes from. Okay, so to summarize, what we have found is that a thin film of coupled topological crystal nanocrystals can have a topological phase like a single crystal of a Ti. The surface state penetration depth is much larger than in a single Ti crystal and can be controlled by temperature, which is absolutely impossible in a single crystal Ti. But in these systems, they can be controlled by temperature. And the penetration depth decreases and the system becomes more topological. The two surface states hybridize less when the temperature increases. The effective spin orbit coupling, so I showed a plot of that. It's in units of magnetic field, it's 25 to 50 Tesla. This is again much larger than in a single Ti crystal where, much smaller than in a single Ti crystal, which is several hundred Tesla. Which means that modest Zeeman fields can be of the order of the spin orbit coupling in these systems, but not in single crystal topological insulators. And therefore you can see an evolution of the Berry phase with the Zeeman field more easily in these systems. And to summarize, this is kind of a phase diagram, T1 here and T2 there. This is the line T1 equal to T2, that's the phase transition line. T1 less than T2 is a topological insulator phase, and it looks like we are working in a region which is in the topological insulator regime, but it's just a little bit on this side of this phase transition line. We don't really know why this should be so, but that's what our work and results suggest. So, so that's the reference for you again, if you want to look at it. Thank you.
Questions?
Yeah.
So just coming back to this question about penetration depth. So in single crystal systems, the penetration depth is much smaller, much shorter, but still you don't see decoupled behavior easily. Whereas in
T2. So in single crystals, the penetration depth is about a nanometer, and so it's known experimentally that if you the thickness of a single crystal is more than about 6 nanometers, then the two surface states actually get decoupled from each other.
I see. Is that what? So I misunderstood what you said. I see. I see.
Oh.
Just a clarification. So you have topological surface states on all sides of each grain.
We do, but since we are sort of only looking at measurements here, so we are only probing the surface states on this surface. But in this, our model will tell you that there should be surface states on all the sides of this entire system.
So you pointed out that the temperature dependence of T2 comes from this charging energy.
Right.
I mean, does the numbers match? Meaning, if you compute the charging energy for a grain,
we don't know these numbers very well. So T1 we can sort of estimate because T1 has to refers to a single grain, the overlap between the surface states of the top and bottom of a single nanocrystal. That one we can estimate. It's about 0.1 to 0.2 EV for these thicknesses of 2 to 3 nanometers. T2 is much harder to estimate. But if you believe this formula, for example, of how how this this formula, for instance, so we can estimate T2 from here. We assume that T1 is 0.1 to 0.2 electron volts, and L is 2 to 3 nanometers, and lambda we know. So that's one way we can estimate T2 from.
So this model looks very similar to the Valens-Burkov model for a Weil semi-metal. How to make a Weil semi-metal is layered topological insulator, and looks.
Yes, but this one doesn't have any gapless bulk states, as far as we can see.
I couldn't see what is different.
States have a gap in this. So that's different from Weil semi-metal, which has a certain number of Weil points in the three-dimensional field also. So this as a function of kx, ky, kz has no gapless points. So I'm not sure where the difference, why there is a difference. Yeah. Yeah. Okay, so what I meant is that as you increase the temperature, the surface states are more and more localized near the surfaces. So the opposite surfaces hybridize with each other less and less. So in that sense, more topological. If the opposite surface states really mixed with each other, you would not call that topological. So this is not a sharp statement. There is no real phase transition that way. It's just how much do the states at the two surfaces hybridize with each other. But yeah, so basically the surface states are better defined as you go to higher temperature. So it's a kind of Coulomb effect. So the idea is T2 involves the electron tunneling from this to this. So it will change the charging energy of both of them. And it'll actually raise the total charging energy of the two of them. So that's like a barrier to this kind of tunneling. And so if you assume that there is some activation form of the tunneling, then you'd expect T2 to increase as you increase the temperature.
right. So actually about that, can you just go back to the formula e to the minus L by lambda is...
Oh, that's the formula for the surface.
Okay.
Yeah.
So then here on the right hand side, then you're saying that the main temperature dependence is coming from T2, which is some activation.
Right.
So if that were true and if T1 is temperature independent, then that gives us a fairly definite temperature dependence for lambda. 1 over lambda goes as A plus B over T
Right.
or something.
So you're asking whether we can fit that to get
Right,
this.
exactly.
Yeah.
How closely does that fit to the observed?
We have not done that actually. We have
I mean,
not-
that was assuming that the gap is, you can talk about it with a fixed gap and T1 is largely temperature independent.
Yeah. So we have not done that. The problem is that all of these are not known very accurately. Like T1 itself has a kind of range. L has L is 2 to 3 nanometers. So none of these things we know too accurately.
Right. No, but I'm just saying that as long as you assume, if that formula is right and you assume that the only temperature dependence is some e to the delta minus delta T in T2,
Right.
then regardless of what the exact value of T1 is, as long as it has some value which is temperature independent, you do have a prediction for
Right.
some.
Right. Okay. So we haven't done that.
Any other questions? No? If not, let's thank the speaker again.